In this video, we will start reviewing the family of autoregressive moving average models, which forms an important class of time series models for modeling individual stationary time series. Let us start here with moving average models. A stationary stochastic process yt is said to follow a moving average of order 1 if it satisfies this model equation over here, where yt is regressed on a constant mu, on the error process, which is our white noise building block, and on the error from the previous time period, so t minus 1. So according to this model equation, yt is a weighted sum of the most recent values of the error terms, sometimes also called innovations. In essence, our error terms include everything that is not captured by our model. So what is new? Through this moving average model equation, we are saying that what we observe today is expected to be a fraction of the new information from yesterday. How could we generalize this moving average of order 1? Well, we can generalize it to a moving average of order q. In our model equation, we would then not only have the error term from the previous time point entering, but also all innovations from the last few time points. And the parameters that need to be estimated are the constant mu and all moving average parameters, θ1 up until θq. Moving average processes can be used to model stationary time series. So of course, the moment conditions for weak stationarity should also be satisfied. In your tutorial assignment, there are actually some additional exercises which you do not need to hand in, but are meant as a good refresher. You will, for instance, run into this exercise that asks you to compute the expected value, variance, and autocovariances of an MA1 process. The end solutions are here actually already provided in between brackets, but I would want to see the full derivations. As you can see from these results, well, the autocorrelation at lag 1 is non-zero for a moving average process, but the autocorrelation at lag 2 is 0. Actually, all autocorrelations at higher orders than the lag are equal to 0. So for an MA1 process, all autocorrelations larger than lag 1 are 0. For an MAQ process, all autocorrelations larger than lag q are 0. If we would be drawing the theoretical parallelogram of an MA1 process, we would be getting this parallelogram, where we have a non-zero value at lag 1 and 0 autocorrelations at higher lags. Of course, in practice, we will never see such a parallelogram, but our autocorrelations need to be estimated from a finite time series. So we would expect to see, for instance, this parallelogram, like the one over here on the right, where only the first autocorrelation is significant and the higher order ones all implode and stay well in between the significant bounds. This is also what you see on the next slide, where I generate a time series from an MA1 process, and I've plotted the corresponding parallelogram. After lag 1, the correlations implode. They become insignificant. More generally, as I already said, for an MAQ process, the first few autocorrelations are different from 0, and after them, they are 0, they implode. So the parallelogram is a useful tool to specify moving average models. If you make the parallelogram of a time series and you see correlations imploding after a certain low order lag, You can take this as an indication that a moving average model might fit your data well, and you can specify the order of your model according to the number of significant autocorrelations you detect.